Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
Today, I wanted to talk a little bit about some of the other blockchains, and I'll do it. I'm not interested in criticizing other blockchains or other offerings. And someone from one of our communities asked if I would do a competitive analysis. I've said the same thing over and over again since I got into the blockchain space, which is I don't really think that the blockchain is about competition, in the sense that I get a feeling from a lot of people, especially Vitalik and Vlad and others, that it's mostly about providing an alternative infrastructure, and that we're all kind of working together.
Yeah, exactly.
To provide that alternative infrastructure. And that's why there was so much collaboration between Ethereum and RChain. We were interested in finding a consensus algorithm that worked. It isn't about competition. And I know that it's very difficult for people in the financial space to not have a scarcity mindset rather than have an abundance mindset. And the one thing I can tell you we have an abundant supply of is work. There's endless amounts of work that we have to get done. That's just if we actually want to take serious dealing with the consequences of how the climate is changing. Beyond that, there's all kinds of work. One of my favorite sayings is art is long, life is short, because there's just an endless amount of really, really fun work related just to the math and the technical aspects, and let alone some of the economic aspects. There are a lot of projects out there that are focusing on interoperability between networks. A good example is, of course, Polkadot. That's sort of their claim to fame, is interoperability. I just want to mention that RChain has, from the beginning, been about interoperability. Part of the reason that I emphasize composition and compositionality as features is not just because that's the only way to scale, and that's how nature scales. And if you look at large-scale engineering systems, you have to build them out of components that you compose together into solutions. Human attempts to scale, as well as the way nature scales, it's all about composition. And if you look carefully at our model for composition, it also provides a model for interoperability. So I want to talk a little bit about that from the perspective of two kinds of issues that you face with respect to trust, and then move on from there to other kinds of security guarantees. Let's just start with the sharding of a single chain. What we're suggesting is that there's a collection of, I'll call them validators. I'm not trying to be too Casper specific, although that's sort of the terminology we use with Casper. So there are some validators, some computational elements that are providing the consensus mechanism. And then we imagine that there's another group of validators that are also providing a consensus mechanism. And we want to be able to have them compose. And that kind of composition is just interoperability, but with some added assumptions about the homogeneity, potentially, of the consensus algorithm. In other words, that the consensus algorithm being used in Shard A is the same as the consensus algorithm being used in Shard B.
When you're talking about the validators from either of these two sets composing, what exactly are they composing there? Is it the consensus algorithm that they're using?
Ultimately, the composition needs to be able to provide a mechanism by which you can have compute that involves actions in both chains. So, for example, a transaction that involves resources in both chains.
Okay.
That will be a consensus about the resources in A, and a consensus about the resources in B, and then some higher level consensus that governs both A and B.
This is across the sharding.
Yeah, exactly.
Yeah.
Okay.
Does that make sense?
Yeah, definitely.
One of the nice things about the way our chain does things is that we can simply assume that we have a bifurcated namespace, right? So shard A is operating in namespace A, and
Hmm.
shard B is operating in namespace B.
Hmm.
And then when we want to combine them, what we're talking about is a composite namespace. That would be sufficient for a wide range of problems. However, there are some additional trust issues that have to be developed. If we just look at it from a purely theoretical point of view, just being able to bifurcate the namespace and then recompose the namespace is a great solution. And by the way, that also works for interoperability. If we say that Ethereum addresses constitute a namespace or Bitcoin addresses constitute a namespace, then if you have a solution that allows you to have heterogeneous consensus algorithms, then the namespace approach solves a big chunk of the interoperability problem. I also want to mention that, hey, we've known this for a very long time. The URIs and URLs represent a namespace-based approach to accessing resources on the internet. A lot of what happens in blockchain is that we forget all the lessons that we've learned in the internet. One lesson that we've learned is, hey, having a name-based access, composable name-based access to resources is an important piece of the puzzle. Another example is that, the last 2 decades from an economic perspective and the internet has all been about the growth of the digital asset markets, whether you're talking GitHub or Spotify or Facebook or Instagram or even, digital finance. It's all been about digital assets. That's where all the growth is. It's really, really straightforward. Data is king. End of story. And if you can't handle large chunks of digital assets, you're not going to compete. Somehow the blockchain markets forget all of these basic lessons that we've learned from the internet. But back to sharding. One of the things that's really key in that approach is that our approach to sharding is an approach to interoperability under the assumption that you can handle heterogeneous consensus.
So the way that you're saying the interoperability could work using this namespace sharding is, like you said, basically like treating all Bitcoin addresses as certain names, or like certain names in a specific namespace, and all Ethereum addresses as names in a different namespace, perhaps. Is that what you're saying?
That's exactly what I'm saying. That is precisely
cool.
The idea. The next piece of the puzzle that you have to have is you have to have, even in the homogeneous consensus setting, there's another thing that you have to be aware of. So you could imagine that a shard, they all collude to attack other shards. So they're all saying, these are the transactions and resources that we've validated so far. And they're doing that in order to hide a double spend and thereby take advantage of the other shards in the network. They only have to do this for a very short period of time. It doesn't have to be a long-range attack in that case. So that's where things get really interesting, because you can't assume, even in the homogeneous case, the same kind of trust model if you're just taking the namespace approach or any other approach. You have to have some mitigation of that risk. The issue is, how do you mitigate that risk? The solution that our chain proposes, and a lot of this came from discussions that we had with Nash and with Mike and Vlad and a lot of others, and I really like Nash's metaphor of the Unix file system.
So each shard, in some sense, is its own chain, right?
That's right.
So like putting a structure on the set of shards is somehow also putting a structure on like the hierarchy of chains. So you're talking about like...
That's exactly right. So then what you do is, at the relationship between parent and child, you set up a double-sided contract, which is effectively saying that the parent's tokens are backing the child's tokens. It effectively gives you an exchange between the resources at the parent and the child.
I see.
And what that does is it ameliorates the risk, because that contract and stitching together all those contracts in this tree, the parent is watching all the children, and so the parent is effectively responsible for any failure of the children, and so on up. And so people who are interested in the security of the network become incentivized to climb higher into the tree in order to gain more security, and they are incentivized to move lower in the tree in order to gain speed.
That makes sense.
And we're talking at a fairly high level because it's very difficult to compare things at a low level. But if you start going at a low level, that's where things really make a difference, because I think Gavin is an amazing engineer. I was really impressed by the Whisper Gossip Network and other work that Gavin has done. So I'm not in any way trying to slag Polkadot or any other project. That's not my aim. I'm as an engineer trying to compare things and what we know with math. Right? So, but if you go to the Polkadot website and their literature, they talk about an aggregation of state machines. The whole reason, the raison d'etre for the invention of CCS and the pi calculus and that whole area of work is because state machines don't compose. And in particular, they don't compose along the lines of machine and environment. Even Mealy-Moore machines don't compose in that way. That was essentially why Milner invented CCS. And when you try to compose state machines, as I learned the hard way, when you try to compose state machines in the way that they do compose, then you get an exponential blow up. And it's very, very, very fast and very bad. So what you end up having to do is to model the constraints on the product space of the states.
Oh, yeah.
The complexity of that goes through the roof. So one of the things that got me into the pi calculus and the process calculi in general was just that we were doing work on relaxed transaction processing, right? So back in the late 80s, early 90s, I was working with a team on the area of what's called relaxed transaction processing, right? So this is, it's more sophisticated than Elliott Moss style nested transactions. You know, so there were a lot of different proposals for these kinds of relaxed transaction models, you know, and the sort of standard cases where you're trying to book a trip, you need to book your hotel and your flight and your transportation. It's okay if the transport doesn't go through, but it's not okay if either the flight or the hotel don't go through, or some combination thereof, right? So it's not like a nested transaction where it's all or nothing.
Okay.
That's the kind of thing. And we were looking at, you know, composed state machines as a way of approaching this. And it was for similar reasons. You know, these are autonomous networks, right? The hotel network is autonomous from the flight network, which is autonomous from the transport network. And you need to get commitment across all of these networks in order to have a successful trip. When we were modeling the composite state machines, I mean, we really did model them. We really did, you know, have them do the product space, state space kind of approach. And that will just bring a computer to its knees. Even with today's compute power, it will bring a computer to its knees in a very, very short period of time. So in other words, it's not scalable. But once you start looking at composing state machines so that an environment is also a state machine, then you have to deal with polarity, what's input and what's output. And as soon as you have this polarity, what's input and what's output between the two different machines, right? That's how the pi calculus arises, under the assumption that your network topology is dynamic. You get a value passing CCS if your network topology remains constant. If you can, as you can in the internet today, send a new URL to another agent, then you are already in pi calculus territory.
This is why I've always been amazed that the pi calculus hasn't already taken over the world, is because it's not just a language of computers, it's a language of the internet.
That's exactly right. Right. That's precisely it. the other piece of it is, as we've explored over the last several podcasts, we get to reason about these things equationally. You know, let's say I went through the Polkadot white paper and I didn't see any equational reasoning. It's pages and pages long, and there isn't a single line of equational reasoning. The row calculus, which fixes the namespace issues in the pi calculus, can be written down in a single page. And whether we're talking about Rolang 1.1 semantics, where, you know, I propose these language features, I propose their semantics, and then I show equationally exactly what they do and why that behavior is the desired behavior for the feature, right? And again, so we have a spec. It's up on the web. You could read it, and anyone, you know, anyone who's a developer, an engineer, can go through those equations as if they were code. That's on the smart contracting side. But over on the consensus side, right? It's like the square root thing was entirely equational. Then we derive equationally a notion of fault tolerance and a leaderless distributed consensus algorithm. We derive that equationally, or the error correcting codes. That again is done through equational reasoning, and it's something that we can verify in a few lines. And it's only then that we have a ghost of a chance of being able to apply formal verification to either the core protocol, or more importantly, and this is where the rubber really meets the road, user-defined smart contracts. At the end of the day, the biggest population of code is going to come from user-defined smart contracts. That will dominate as your sources of error. You could have angels from heaven write your core protocol, and it doesn't matter. Because all your security exposure is with those lousy humans.
What if you just ask everybody to double check their code first?
If we look at things like the DAO bug, the DAO code was audited and they didn't catch the bugs. The same is going to be true over and over again. You can have really, really crack developers and really, really crack auditors, and you're just going to miss things. It's the nature of systems of this level of complexity. You have to have support to catch these errors, and the more the complexity rises, so as you start adding heterogeneous consensus algorithms, then you have to have equational means of reasoning about how the different consensus algorithms compose, so that you get end-to-end notions of consensus. And you have to have behavioral types that allow you to see, at least to some approximation, the behavior of the various contracts that are running within these heterogeneous environments. And the nice thing is that a behavioral type can abstract away the behavior of a contract that's running in a remote chain. One of the things that I have long proposed since 1996, no, earlier than that, 1993, when I was doing a research stint at British Telecoms, I proposed to use behavioral types as a discovery mechanism. So a service can say, I need a service that meets the following type, using a form of residuation, which you can think of as like a kind of division operator in logic. You can go and find things that meet a spec up to a delta, and then go and find things that will fill the delta, and you can do this recursively. Using behavioral types, you can layer over a heterogeneous system of networks a discovery mechanism to stitch together contracts that will provide a service. This is like what I would like AI to do for me. I would like AI to write code by assembling code out of the chunks of code that are out there.
So just to clarify, you're saying like you have some sort of spec for a service in mind, and then you can search for existing contracts that may be able to you may be able to put them together in a particular arrangement to fulfill this spec.
That's exactly right. That is precisely
interesting.
yeah. And I've talked about this before, but it's worth restating. If you think about a model checker or a type checker and sort of turn it on its side, it becomes a query engine in the following sense. I've got all these programs up in some data source like GitHub, for example, and they're in a language that I know how to model check or type check. So I send in a spec, which is, a particular property or a particular type. And then I go and I brute force check every single program in the repo against this property.
Right.
And the ones that match, the ones that satisfy the property, those are the ones that I return as the response to the query.
Yeah. So you just like filter the database by this particular property.
That's exactly right. The first refinement of this idea is to recognize that type systems don't give us a lot of useful searches. So Mike Stay has a really good example of this, which is if you just look at ordinary functional types, like the kind you might find in Haskell or Scala or whatever, sort and shuffle have the same type. But they do the opposite of each other.
Right.
Yeah.
Right? Searching on the basis of functional types is not going to get us very far. But searching on the basis of the behavioral types, whether we're looking at the Kairos style types or session types even, which are slightly weaker than Kairos style types, that's going to give us a lot more information. In particular, the Kairos style types will give us information about the structure of programs. If you look at the way Ladle, for example, generates a logic of monoids even, we can detect things that are prime or not composite using that style of type. And that notion of primality corresponds to single-threadedness in the pi calculus or the row calculus. So you can actually search, you can say, well, find me all the programs that are single-threaded. Right. Or the other way around, more likely, that you've got a concurrency bug somewhere. Find me all the programs in my current repo that are multi-threaded and have some other property. That's going to give you some candidate culprits to go investigate.
Yeah, you can test the race conditions.
For example, that's a really good example. This gives you a fairly decent discovery mechanism. Now, the piece of the puzzle that we haven't talked about in this is, so you can imagine that you can satisfy a type up to some delta. It's like, well, this satisfies most of your type. And there's a notion of residuation that's at play where you're saying it satisfies a kind of implication that involves your type. And now what you need to do is to go find something that will discharge the hypothesis of the implication. That's the dependency that you need in order to do that. And that gives you the basis for a discovery mechanism where you assemble across this heterogeneous network of smart contracting chains, contracts on the fly, which is where I think we ultimately need to get to. Rolling back from that idea, you can imagine that, some contract wants to depend upon another contract that runs on a remote chain. That contract is they're written in just heterogeneous languages. But that's okay because at the level of type, and in particular Kairos or behavioral style types, you don't care what language the thing is written in. All you care about is that it satisfies certain properties with respect to the sequencing of I/O.
Are you having to compile into Rolang first in order to determine the type?
The nice thing is that you let the remote chain semantics provide that. At the end of the day, you're trusting their consensus algorithm, you're trusting a whole bunch of things. You have to trust that chain's attestation that smart contract satisfies a particular type. And then you go and satisfy yourself that the way it gets to that attestation is a computation that you respect.
Okay.
Does that make sense?
You're talking about like you're querying into other chains that are using other languages and they return back ones that they have determined to fit that.
That spec. That's exactly right. Yes.
If you aren't already working or providing them with your system, how do they determine?
So all they have to do is to have the type checking mechanism between an agreed upon type of property language and whatever languages they're expressing their terms. That can be done by a compilation to a common sublanguage, or it can be done in a number of other ways. So your proposal is a particular implementation, and I'm trying to be more abstract. I'm trying to say, well, if they implemented it in Rust, we don't care as long as they have a type checker. That, or if they implement it in Go, we don't care as long as they have a type checker. And then it's up to the community to say whether or not that particular type checking algorithm is respected. Right? That part of it has been vetted.
It almost seems a little implicit because you are using the data from this chain, right? So you do have to trust all the aspects that go into it, I guess.
Well, yeah, by the time you're talking about chain interoperability, especially if you're talking about smart contract chain interoperability, you're already kind of there.
Right.
So kudos to Polkadot for recognizing that data is king. Like if you look at their literature, one of the things that stands out is how much of their market analysis coincides with our market analysis. At the end of the day, data is king, and this will matter enormously if we want to have adoption of the blockchain. All of the major players are waiting to see one application other than trading of tokens on top of the blockchain. And if the blockchain continues to be optimized just for token moving, then I think it's setting itself up for a feedback loop that will make it will be very hard to escape, right? Because the more it's optimized for that, the harder and harder it gets to be a data transfer network.
Yeah.
And so even if you have the greatest interoperability protocol in the world, if the only things that are interoperating are things that have been optimized for moving tokens around, there's no data in that network. You have to seed such a thing with a data solution that's scalable enough and fast enough. And that's where our chain, that's where we landed, was you have to have at least one chain that handles data and also handles sharding, and then extends the sharding solution to an interoperability solution. That feels like a more natural way, because then you're guaranteed at least one of those things is providing an escape path from token to data. That's mostly the things I wanted to say. I mean, there are other chains that we could talk about. We could talk about Algorand, we could talk about Holochain, but a lot of the criticisms apply. It's the same kind of critiques. At the end of the day, what we're really demanding, and I think everyone has to demand, is that we have a level of verifiability with respect to the operation of the chain that is just the new standard. I mean, I don't know how to put it any other way. We could think of the last 2 decades of the internet as exploring all those applications where if you failed, it would be kind of okay. If Google Maps doesn't serve you up, the right map the first time, it's kind of okay. Certainly if Facebook doesn't push the cat memes out, that's certainly okay. We don't care about that. Or if Spotify, doesn't deliver the right song the first time, that's okay. Nobody's going to die. But we're kind of coming up to the end of those markets in some sense, mostly because we're running out of time with respect to how to address climate change, but that's a separate issue. We're now at a point where we need to consider mission critical applications, and we need to consider the internet style applications as mission critical applications. Society is not going backwards to a time when it doesn't have the internet, or at least it doesn't want to. We need to think about this next wave of applications in the light of Six Sigma style stuff. Is your software so good that if it were an air traffic control system, you'd put your daughter on that plane? If that's your measure, if that's your bar, then you need to have a level of formal verification. The first thing is you've got to be able to grasp the proofs. That's why I really look for equational reasoning, because as soon as the proofs get all fiddly and lots of English language in them, it's an older style of mathematics. The modern style of mathematics is much more driven in a way that we can automate it with theorem provers and model checkers. So that's what you're driving for, and you should start to see that, right? I mean, that's what I've been trying to argue for in a lot of these talks is, here, look at the row length spec. Yes, I could go and code this up in our favorite theorem prover, but I would just want you to see the equational reasoning. Look at it. It's graspable by ordinary people. And that should be the first sign, is that you start to have these lovely specs that are clean and beautiful. And then right on the heels of that, and look, we've got a theorem prover that's verifying our work. And at that point, then we can start to talk about mission critical applications.
Yeah, I mean, for me, that's always been the draw of the RChain project is that you guys are talking about equational reasoning and, this correct by construction and compositionality. I mean, that's what I feel like all of these projects need, honestly.
I absolutely agree. But it's a funny thing because it is a blind spot. I was talking with someone yesterday, and I was just pointing out that people shouldn't feel bad or embarrassed or even that it's weird that we don't have a lot of compositional reasoning in a lot of prominent formalisms, because we don't. It's been a blind spot in human cognition. Thinking that way takes a particular turn of mind to start to think that way. I've made this point over and over again, but I think it bears repeating. Quantum mechanics, at least as initially formulated, was not compositional. General relativity, not compositional. And these have really, really big consequences for those theories. And the reason I use those examples is because they're sort of the pinnacle of scientific achievement in terms of accuracy and predictive power.
Right.
In many ways, they're our gold standard, and they're missing this feature. If you think about them as code bases, they're missing this feature. So it is a new way of thinking to think compositionally, but it's the only way to get to scale.
In general, like with some of the big chains, each of these systems is going to have its own chain.
Mm-hmm.
And it's going to be less common that they go out of their way to form some kind of subchain in another system. So when you talk about within our chain having these shards from Ethereum and other places, is there some way that...
I think I understand your question.
Yeah.
So there are certain things that we need to get clarity on. Number one, you can have our chain mount Ethereum. So our chain treats Ethereum as a child, right? And our chain shard treats Ethereum as a child. You don't need Ethereum to do anything special, right? It's just that you've got an Ethereum contract on one side that's being backed by an ArcChain shard on the other. So there's some Ethereum resource that's backed by some ArcChain resource. And all the Ethereum dApps that use that particular resource, they're able to do a particular kind of exchange, and vice versa. That's assuming that the resources are effectively ERC20 tokens. If you want to do RChain and Ether, there's a little bit more work, but it can also be done in this style without a lot of invasion.
Yeah.
If you want Ethereum to mount RChain, that's a lot more work. From my point of view, that's great because it basically puts RChain in the glue interoperability seat, which is ultimately where you want to be. Ultimately, that kind of landscape is tilted in such a way that all the value rolls out of Ethereum and into RChain.
Yeah.
But the other thing I want to point out is that, there's no reason why you can't have multiple Ethereum networks, right? You just start up a collection of Ethereum nodes and they talk to each other, and they're, you already have that, right? You have Ethereum mainnet and you have various Ethereum test nets. It's only that people recognize one of those networks as the one true Ether.
Yeah.
Right? But in point of fact, you could have, red Ether and blue Ether and, green Ether, and they could all be mounted with respect to each other in such a way that, red Ether backs blue Ether, for example.
So is a way that the value starts flowing in this direction? Is a reason why an Ethereum person would come over to the RChain be that RChain starts developing more serious applications first, and then?
Yes, there are two main reasons. One is they start to see that there's much greater performance in RChain, and then the second is because there's greater performance, people are starting to build applications there. CryptoKitties doesn't bring RChain to its knees.
Yep.
On top of that, there are all kinds of other reasoning. Another example is that, we've measured what it takes to build applications that are serious about data. The RCat backend for RSong and other things enables applications that are data intensive to get to an MVP in about 6 to 8 weeks with 2 engineers. If you think about it, right, that's about the kind of resource outlay that most projects spend on writing their white paper.
Yeah.
But instead of writing a white paper, they could be actually producing running code, which demonstrates the point of view. And we think that that alone could be one of the things that reinvigorates the RChain space. Because I think a lot of developers have left the blockchain space in general because the money has drained out of it in some sense. It's no longer gold rush mentality. It's a different kind of approach, a different kind of space now. And if you want to get more dApps involved, you have to show them that there are opportunities for them to be able to write applications that will meet markets that demand things.